All right. So on Monday, we talked about 6.1. And in 6.1, we talked about how the area between the curve and the x-axis that we'd been looking at was actually only part of the problem. And in other words, when we were thinking about the entirety of the problem, it turns out that we were always looking at sort of the area between two curves, except that we learned it only as like one curve minus 0. And so we were able to kind of extend that idea of finding area into different shapes and not only doing things with respect to x, but also with respect to y. And today we're going to shift gears a little bit, and I think it'll make a lot more sense when we come back on Monday of next week to sort of tie together what we learned on Monday with what we learned today. Okay, so this is going to feel a little bit different than what we did on Monday, but it's really laying the foundation for those connections between what we're learning, what we learned this week and what we're going to learn on Monday. Okay, so think about this more as a connecting piece. All right, so in 6.2, we are now going to be talking about volume. All right, so we are not talking about area right now, but we're now talking about things in 3-dimension or volume. And so as we can see from the what we know and what's new, what we know is that if we take an integral and we have some function here with respect to x, we will get the area. Okay, and so that's what we've been finding, is we're finding the area between the curve and the x-axis. We're finding the area between the curve and the y-axis. We are finding the area between two curves. And so this decision making is something that you do want to make sure you feel comfortable with. Okay. How do you know to use dx or dy? Okay. So as you're going through the quiz for this week and as you are studying for that very last exam that we have in about 2 weeks, you really want to think about this decision-making piece. How do you know to use dx or dy? Okay. And what we're going to talk about today, we're going to at least sort of get started with this, is now instead of finding the length or those purple lines that we were drawing on Monday, what we're going to now be finding is when we integrate area, we're going to get volume. And we could do this with respect to x, or we could do this with respect to y. But the big takeaway here is that if you integrate two-dimensional things, you'll end up with 3-dimensional numbers. Okay, so our number is going to reflect a 3-dimensional space rather than a 2-dimensional one. Okay. And so now things are going to get exciting, right? So today, my hope is that we're going to focus on something called volume by known cross sections. Okay. And so I think pictures are definitely a very large part of this unit. And so we're going to take a look at these pictures, take a look at some shapes, and help ourselves remember some area formulas from way back when. Okay. We've used quite a bit of these over the course of the year, but I think it'll be nice to have these area formulas kind of front and center. Okay. So let's take a look at this green sort of paperweight looking thing. Okay. Now it looks like a hemisphere, but each of the slices that we have here, let me see what's a good color. Maybe pink. All right. So if I think about this slice, what shape is that slice? All right. And so if we kind of imagine that's the first slice, maybe here's like a second slice. And we have sort of another slice back here. Okay. So each one of these pink slices are semicircles. Okay. So Josh and David, you are correct. These are semicircles. And I'm wondering if you can tell me what the area formula for a semicircle is. All right, and so if we jot that down, we've got area equals pi r squared, but we're going to put that over 2 because we only have a half a circle, okay? Now, if we're thinking about, oh, well, we might be integrating things, what are the constants in this equation? Oops. What are the constants in this equation that we would want to sort of pull out to the front of our integral? I agree, Graham, pi and the 2, perfect. And so maybe we're just going to write this equation as pi over 2 times radius squared. Okay. Same formula, just thinking about how we might be able to use it when we think about integrals. All right, so we have a semicircle here. What about here? What are these cross sections? Yeah, these ones are quarter circles. So quarter circles. All right. And so how would we modify our equation for the quarter circle? Right? What stays the same? What changes? Good, good. So we're going to have pi r squared because that's the whole circle. Exactly. We're going to divide by 4 instead of 2. And if we again think about how we might want to set this up for the integral, we can bring the pi over 4 to the front, and then we'll take the integral of that r squared. Okay. Before we take a look at the other shapes, I'm wondering if you can maybe annotate on here real quick. Where is the radius? Can someone draw a radius on the green semicircles or draw a radius on the blue quarter circles? Where are those at? All right, I see one radius there. I do see that one, Yithan. I wonder if there's a different way that you can draw that. Yeah, there we go. There we go. Okay, so if we look at the 2 radii, let's see, Graham has drawn this as one radius and Yitan has drawn this as a second radius. So in the quarter circle. Now, in the first one, in the green one, does this radius go all the way across the base? Like this radius right here, does this go all the way across the base? No. Okay. What about in the quarter circle one? Does this radius go all the way across the base? All right. Let me, it's a good color. Okay. So when we say base, all right, if I were to draw the base in the green one, I'm really looking at this. in the yellow. Does everybody see that base? So the yellow circle-y area that I just outlined, that's the bottom of this shape. Okay. Now, if I think about the radius that Graham drew, it was sort of like there. But that radius, it didn't go like all the way across. It only went like halfway across. But if we sort of apply the same reasoning to the quarter circle one, if I draw the base like this, and then I think here's the radius, would we say that the radius goes all the way across? Yeah, okay. So when we look at these shapes, it's really important to think about how the specific side length or radius in this case compares to the whole bottom of the function. Okay. All right, let's move on to this third one. What shape in the yellow would you say these cross sections are? Rectangles, there we go. Rectangles. That's not how you spell rectangles. Rectangles. Okay, all right, so rectangles, and the area formula for a rectangle. Length times width, good, length times width. All right, I'm not going to use yellow for this one because I don't know that we'll really be able to see it. I don't know, can we? We kind of can, okay. So I have this as the base here. If someone were to draw maybe the width and then the length. So here's like one rectangle. And the rectangle is kind of like sticking up from the bottom. Would you say that the bottom of the rectangle goes all the way across the base or halfway across the base? All the way. Good, good, good. Okay. Now, these are important questions to ask yourself as you're imagining these pictures, okay? So let me pause here for a moment. We've taken a look at three shapes so far. We've got all three of these shapes. I know that they're all different, right? We've got semicircles and quarter circles and rectangles. But what are the bases of all of these shapes? Like the bottom part of the 3-dimension. Are those shapes the same or are they different? Yeah, they're all the same. And so these things that we outlined in the yellow, like this is the bottom, turns out it's actually the same as this one. Turns out it's actually the same as this one. Okay, so all three of these have a circular base, but the shape that comes out of this circular base, all of those shapes are different. Okay. How are we feeling so far about this? I know it's not even 10 in the morning and now we're like 3-dimensional things, yay. So maybe a quick thumbs up or a thumbs down or send me a message. How is this feeling so far? I know for me, like at least the visualization is kind of tricky sometimes. Okay. Okay. Now we are going to layer on functions to all of this, and we are going to compute things with this. And so I really want to make sure we're okay with the concept behind it. Okay. All right. So we've got semicircles, quarter circles, rectangles. We've got all those area formulas above. Now let's take a look at the bottom three and figure out what we can recognize about these, okay? So this fourth one right here, I would say that these are, yes, they are triangles, but maybe more specifically, we could say that these are isosceles triangles. Anyone happen to remember what isosceles triangles are? Like what makes them so special?
Two sides are the same.
Perfect, exactly, two equal sides. And so in particular, notice again that we've got sort of this circular base, right? But if we draw just one of the slices, we'll notice that we have a right triangle and that this leg is the same as that leg. Okay, so just kind of look at that for a moment, see if that makes sense to you. And we might say that our area here is going to be 1/2 base times height. And if we think about a constant we would want to pull out to the front, maybe it's just the 1/2. Okay. All right, two more pictures. Both of them have a circular base. All right, so there's one circular base. There's another very badly drawn circular base. And in both of these cases, we've got triangles, okay? And we've got triangle. Now, in both of these cases, do you think that the base goes all the way across, like the bottom of the triangle, does that go all the way across the base, or does it only go halfway across the base? For the pink triangles, all of those pink triangles, yeah, that base goes all the way across, okay? And so in these cases, we can use the same formula, area equals 1/2 base times height. But we want to be really thoughtful though, because we're going to get sort of the base down here, but the height has to be perpendicular to that base, okay? So we want to make sure that we know how to find that height of the triangle, because it's a little different than the isosceles right triangle case where we're given that height, okay? But today we are going to take a look at semicircles, quarter circles, rectangles, and triangles, and think about how we can find the volume of these shapes. Okay, so that's what we are about to do right now. All right, so all of these examples intentionally have no diagrams with them. Okay, kind of like on Monday, we were drawing our diagrams that go with them. In the quiz though, quiz 14, I believe I do give you the diagrams to help you kind of visualize them a little bit. But I think it is an important skill to know how to draw things just like we did for 6.1, okay? So we're gonna set things up by drawing a picture. We are going to find intersection points as we need, and then we're going to do an integral. So the 3 steps are very similar to what we had on Monday, except now the thing we're integrating is already in 2 dimensions. So we'll be able to integrate it and now make it three-dimensional. All right. So let's get started with these diagrams. Okay. Let's see. Maybe we'll go with green. F of x will be green. And g of x will be orange. All right. Tell me what you know about f of x. Tell me what you know about g of x. F of x opens up, g of x opens down. Exactly. So we know this one opens up. We know that this one opens down. All right, give me a little bit more information that might help me sketch this more accurately. All right, can we be a little bit more precise in that? All right, perfect. Nice job, Graham. Nice job, Brian. We are shifting down 3 units for f of x. This is down 3 units, and this one is up 5 units. All right, so now that we know those, let's go ahead and sketch those. All right, so I know that I have one parabola that kind of, oh goodness, looks something like this. And then we have the other parabola that looks something like this. Okay. And we know that this point up here is 0, 5, and that this point down here is 0, -3. Okay. So we've drawn a sketch of our diagram, but what would be really helpful is if we could figure out the intersection points. And so in particular, what is the coordinate here and what is the coordinate here? Okay, so based on Monday, how do we do that? How do we find that intersection point? Set them equal to each other, exactly. And so to find intersections, we're gonna go ahead and let x squared minus 3 equal 5 minus x squared. So here's our orange function. Here's our green function. All right, set them equal to each other. How do we do this? How do we proceed from here? Moving the right to the left. All right, I like that. So I'm going to add x squared to both sides. So I'll end up with 2x squared. I'm going to subtract the 5. So I get -8 equals 0. All right. And then it is a factoring game. So 2x squared minus 4 equals 0. What is our shortcut that we should know? And by should, I mean, not shame on you if you don't know it, but it's going to be so helpful for you if you do know this. What do we get when we factor? All right, so x minus 2, x plus 2. Very nice. Okay, this structure shows up a ton. In fact, I think factoring and completing the square come up a lot in Calc 2. Okay, so that would be like a good skill to kind of write down and practice a little bit before Calc 2. But we have this, and we're able to find that our intersection points are x equals 2 and x equals -2. Okay, and so we know that this point has an x coordinate of 2, and we know that this one has an x coordinate of -2. Now, how do we find the y values that go with them? Plug it into F and G. All right, it doesn't matter which one though. It should give you the same answer either way. So decision making, which one might be easier? Okay, I agree. Great decision making. Let's plug this into F and see what happens. So 2 squared is 4, 4 minus 3 is 1. So I know this has a y value of 1. I know this has a y value of 1. Okay. So we've got our points. Now, before we set up our integral, let's draw some lines. Okay. So looking at this picture and thinking about what we learned on Monday, does our instinct tell us we should draw vertical lines or horizontal lines? What are our thoughts? Vertical lines or horizontal lines? And we could maybe use the equations to help us decide. Okay, see quite a few guesses for vertical. All right, well, let's double check these equations real quick. I've got basically y equals a bunch of things with x, y equals a bunch of things with x. And if I draw those lines this way, no matter how many I draw of them, do they all have the orange curve on top and the green one on the bottom? They totally do. Okay, so that right there is our decision-making process. Now, let's say that you totally missed Monday's lesson. You're like, I don't understand how people know that it's supposed to be vertical, and you try drawing them horizontally. I bet even after drawing one of them, you would realize that's not going to work out for us. But can someone explain to me why this might not work out? Like, why is it not helpful if I draw lines this way? Like, what's the problem with that? Exactly, because the left and right function are going to be the same. And so if we were to draw one this way, we would have green minus green, which would give us 0. Or if we chose a line this way, we would do orange minus orange, and that would give us 0. Okay. And so these instincts are good. Let's draw one of these lines. All right, here's a bigger one, here's a small one at the end. Okay, and so all 3 of these, there's an infinite number of them, but of the 3 that we've drawn, all 3 of them have the same top function and the same bottom function. Now, these lines, what do they represent in our question? What do these purple lines represent? Because on Monday, they represented one thing, but here they actually represent something else. Okay, base of S. So this, it is the base, okay? Now, if we kind of bring this back to, well, that's making it pretty small. If we bring this back to some of the questions or the pictures on the previous page, which one of these pictures do you think represents what we're drawing the closest? Yeah, the third one or the rectangles one. Exactly, exactly. We didn't draw this in 3D though, right? Like there's a reason why I grabbed some photos from the interweb here, because for me to sit and try and draw these as well as this computer generated graphics did, I think I would leave you all much more confused than actually making any sense, okay? But here's what we have drawn. We've drawn this part, the flat part on the bottom, okay? And these purple lines that we drew is this part. That's like one purple line. Maybe this one here, that's another purple line. Maybe this one here, that's another purple line, another purple line, another purple line. So what do the purple lines represent? If these things that we just highlighted here are the same as the purple lines in our diagram, what does the purple line represent? So if you say rectangles, then that would be like the whole thing. Ah, okay, so it's like one side of that rectangle, right? Yeah, in particular, it is the base of one of those rectangles. It's the base of a rectangle. It's the base of a rectangle, okay? So it's not a square, it's not a rectangle, but it is one of those side lengths, all right? And so when we go down to our diagram, I find this really helpful to write out for myself what that purple line represents, because sometimes that purple line is going to be the base of a shape. Sometimes it's going to be the base of a triangle. Sometimes it'll be the base of a square or a rectangle. Sometimes it'll be a radius. And because that changes, it's really valuable for us to practice visualizing what that is. Now, if we look back to the problem though, it says that the cross sections perpendicular to the x-axis are squares. So these purple lines represent, where do I write this? The base of a square. Okay, so the base of a square, or one might say the length, let's say side length of a square. Okay, so the base of a square or the side length of a square. All right. So we are finding not the area, but the volume. And since we're finding the volume, we don't want to write A equals, we want to write V equals. Okay. Now it turns out that if we take every single square in here, we take every single square, we find the area of every single square and we add them all up together. We'll get the volume of the shape. Okay, let me say that one more time. If we take the area of every single square in this entire region and we add them all up, we will get the volume of the shape we want. And so the way we're going to do that is we're going to say volume equals the integral, the integral of area. Okay. Now, one last thing I need to fill in before I start plugging in numbers. These purple lines, are they stacking along the x-axis or stacking along the y-axis? Along the x-axis. Good, good, good. Since they're stacking along the x-axis, should I have this with a dx or a dy? Yeah, dx, good. So integral of area dx. All right. All right, so in order to answer this question, I need to know an area formula. I need to know an area formula for what shape? For a square. Okay, we could say rectangle, but why are we saying square in particular? Right, we know from the question that they're asking about squares. All right, so they're all the same side length. All right, so my integral of the area. So what I need to do for the area, what is the area formula for a square? Side length squared. Okay, I'm going to even write that in words right now. Side length squared dx. I bet we can fill in our a and our b value as well. What should my a and b value be according to the picture? Like, where do I start counting these purple squares and where do I finish? Yeah, exactly. -2 to 2. Because we're starting here, we're drawing little rectangles all the way until we get to here. Okay, so we're starting at x equals -2. We are stopping our square counting at 2. Another way that you could have guessed this is if I have dx here, these numbers in the bounds, should they be x values or y values? Yeah, they should be x values, right? If I have dx, I better have x values as my bounds. Okay, well, we've got like one more step to figuring out our equations here. So how do I find the side length if this is a side length? How do we take what we learned on Monday to find out how long this purple line is and how long this purple line is and how long this purple line is? Okay, so we're revisiting that theme from Monday, which is if we have two functions like this that are sectioning off a given area, we want to take the integral of the top function minus the bottom function. But when we plug that in over here, we're going to have 5 minus x squared minus x squared minus 3 dx. Correct or incorrect? All right, we've got 1 vote for correct, that this formula matches this formula. All right, any other guesses or thoughts about why it's correct? Correct. All right, we've got 2 votes for correct. Any other thoughts? All right, well, y'all are wrong. Damn, I know. Because your formulas don't match. Ah, all right. Eagle eye over here. Indeed. This equation says side length squared. That's the area formula, side length squared. All you did is say, I want to find the side length, and then I'm going to integrate. That would give me the area, but I don't want area. I want volume, right? So that same decision-making process is part of this. However, we have to match the area equation. So if it's side length squared and this is our side length, then we sure better take this and square it. All right, does that make a little bit more sense how we need to match the 2 equations here? So we really need to think about that area formula, okay? That's why it's so important to say, this purple line that you drew, what does it even mean? Because you're going to use that inside of an area formula so that once you apply the area formula, then you can find the integral. Okay, so if you are not using an area formula to find volume, something went wrong. All right. Okay, so let's continue. Thoughts, can we use symmetry here? Yes, okay. So what do we want to choose as our new bounds? 0 to 2, great. And then we'll go ahead and double that, right? So we could say the integral from 0 to 2, and we'll double that. And while we're doubling that, let's go ahead and simplify what we have in here. What goes inside those purple brackets before I square things? All right, when I simplify that, what do I get? Negative x squared, super close. How do we change that? -2, there we go. So -2x squared plus 8. All right, now I have to square this. And if I see anyone write this, I'm just gonna stop grading your question and give you a big fat 0. I'm just kidding, I won't give you a 0, but why is this so wrong? Yeah, we didn't FOIL or we didn't multiply it out, right? So these are the things that, like, the small things that used to be small when the only thing you had to do was FOIL. But now in the context of a bigger problem, when you forget to FOIL, and then you have to integrate, and then you have to plug in numbers, now your whole answer is totally off, right? And so it's really important that we recall all those small algebra pieces. And so when we FOIL this out, we should get 4x to the 4th minus 2 times 8 is 16, 16 times 2 is 32, x squared, and then plus 64 dx. Okay, so now that we FOILed it out, now we're good to go. Okay, so before we crank through the rest of this process, are there questions on what we've done so far? Because I think all of this stuff is the hard stuff. After this, you just have to rinse and repeat and find your integrals, plug in some numbers, and call it a day. Sort of, not quite, because if we were using x and y values, we would have like both x and y values in here. Yeah, I think you could say that. Okay. Yeah, so if you want to have a three-dimensional answer like volume, then you should be starting with an integral of a two-dimensional thing. So the two-dimensional part is the area formula part. That's the part that gets us the two dimensions, even though we don't have a different variable for it. Okay. All right. So what is the integral of this expression? I'll give you a moment to kind of type that in. What is the integral of this expression? Right, let's see, 4x to the 5th over 5 minus 32x cubed over 3 plus 64x. Good. So 4x to the 5th over 5 minus 32x cubed over 3 plus 64x. This is a lot of gross fractions. I'm super glad we decided to use the idea of symmetry so that we could sort of make our calculations a little bit easier. Okay. And so I'll leave those computations to you in the privacy of your own home. But at the end, you should end up with this. Okay, so plug in some numbers, be accurate with your computations, and you should end up with 2048/15. Haha, I see what you did there. It is a voluminous number. Sometimes though you get an answer of like 1 and you're like, seriously, the answer is 1? But yeah, sometimes it can be. Okay, let's do this. I would like to set up a different one, okay? We will set up in the sense that we will draw some pictures, we will find some intersections if we need, and then think about this area part. Like, what is the formula we need and how do we find what that purple line represents, okay? So let's take a look at example 2. All right, example 2 says, compute the volume of the solid whose base is the region between f of x equals 4 minus x squared and the x-axis. There should be no second and. Whose vertical cross sections perpendicular to the y-axis are right isosceles triangles. Okay, so we're going to start by drawing some pictures. We're going to think about intersection points as we need them, and then we will think about the rest of our decision making. Okay, so let's get started with the picture. All right, tell me what we know about f of x. I'm gonna pick the easy one here and tell you that is your x-axis, but somebody else tell me about f of x. What do we know about f of x? Upside down parabola, vertex is 4 units above. Perfect. All right, so let's sketch that in. Okay, so let's go ahead and think about the directions of the purple lines that we should draw here. Okay, so read the question and tell me which way our purple lines should go. Should they be vertical or should they be horizontal? And most importantly, how do you know? Okay. All right, so horizontal because it says perpendicular to the y-axis. Okay, there it is, right? These cross sections are perpendicular to the y-axis, so I better draw them perpendicular to the y-axis. Okay. Now, that probably goes against all of your intuition, right? We would have probably looked at this picture and said, I want to find the vertical lines because there's a green function that's on top and an orange function that's on the bottom. And then maybe we could use symmetry because the right and the left will be the same. Okay, all right. So before we set up our integral, let's find out some of these important intersection points. And so in particular, I know that we said that this one was 0, 4. What do we have for this point and this point down here? Okay, and so what are they? These numbers have been chosen to hopefully be nice numbers for a Wednesday morning. What do we have for those x-intercepts? There we go. 2, 0, and negative 2, 0. Perfect. Okay. So we've got these intersection points. Now let's think about intersection points. So we did really 4 minus x squared equals 0, and then we got x equals plus or minus 2. So here's the x-axis, and here is the green function. Okay. All right, now these purple lines, okay, before we set up our integral, where we know that volume is the integral of area, we need to make a few decisions, okay? So this purple line, any of the purple lines, what does that represent? What are our guesses? What do those purple lines represent? There we go. One of the 2 feet of the triangles. Yes, it is the bottom of a triangle. Okay, so let's kind of hold this in our heads for a little bit. I'm going to scroll back up to the pictures we looked at originally. Okay, so we're thinking triangles, and in particular, right isosceles triangle. So if we scroll back up, we might think this is really what our picture looks like, okay? But we've only drawn this part. We've only looked at the bottom, the base, and what we're finding is that all the way across the base, that is one of the feet, maybe we mean legs, one of the feet of the triangle, okay? And in other words, we could even say that that is the base of a triangle. But since it's isosceles, the base is actually the same as the height, right? So if we know the base, then we know the height. All right. So based on what we have so far, what we can write down is that this is the base of a right isosceles triangle. Okay. Now, knowing that these bases, I'm sort of starting the base, like the biggest base would be down here all the way to like the tiniest base at the top. Should we say this is the integral of the area dx or the integral of the area dy? There we go. All right. We are indeed stacking these up the y-axis. Okay. I'm going to write that here. The dy is because we are stacking up the y-axis. Okay. Stacking up the y-axis. Now that also means that my bounds, like when I start to plug in my a and my b values, those a and b values should be y values, not x values. Okay. So what might we want as our bottom bound here? What might we want as our bottom bound? In other words, where do we start counting our triangles from? 0, okay? And if we start counting at 0, where should we stop counting triangles? 4, awesome. So from 0 to 4, my bounds are now the y values here, okay? Since we're doing dy, the bounds should also be y values. Just like when we do u substitution, typically the bounds are also u values, okay? Now, we know that the area of an isosceles triangle. What is that area formula? Area formula for an isosceles right triangle. 1/2 base times height. There you go. So I'm going to put 1/2 base times height dy. Okay. Now in the next line, I'm going to go ahead and bring the 1/2 out to the front. I know any constant I can just bring out to the front. So the integral of 1/2 times the integral from 0 to 4. Now we need to find an expression for the base. And then we need an expression for the height. So we're just sort of setting that up, okay? We need an expression for the base. We need an expression for the height. Now, if we think about these purple lines, right? One of the problems that we have about these purple lines is they go from green to green. So how do we figure out what that is? Okay, green to green, green to green. One way in which symmetry can be used. So this is a different way of using symmetry, okay? So Yuthan, you were spot on in thinking maybe we could use symmetry. The way we use symmetry here is like this. Ooh. We know that this distance is going to be the same as this distance. We know that the right-hand side distance is going to be the same as that distance. We know that this squiggly part is going to be the same length as that part. And we know that this squiggly part is the same as that squiggly part. So we can use symmetry by saying, let's find these sides, the squiggly parts. And if I take the squiggly part and I double it, I will get the whole base. Okay, let me say that one more time. If I take the squiggly part and I double it, I get this whole length right here. And so that is what we are going to do, okay? We are going to double some things. We're going to double something. We're going to double something else, okay? So if this half is the same as that half, then another way to say that is this half. If I times 2, it will give me this whole distance. Okay, and maybe it's easier if we think about it with numbers. How long is this distance? Like this distance right here from, yeah, that's 2, right? Okay. How long is this whole distance? 4, okay. So you did 2 times 2, which gives you 4. Let's say that this distance is 1. How long is this distance? 2. Okay. So 1 plus 1, you can add them, but multiplication is the same as saying times 2, right? 2 times 1 is 2. Yes, there we go. That's the structure. Let's say that this length is 1/2. How long is this whole piece? Good. And I could say 1/2 plus 1/2, but since we're trying to multiply things here, we could also say 1/2 times 2, which will give us 1. Okay, so what we're going to do to get around the fact that we don't know how to write this as an expression is we're going to find half of it and we're going to double it so that we can find the whole thing. Okay. My equation is y equals 4 minus x squared. But on Monday, when we talked about things with dy, we said that typically the equations are like x equals blah, 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 blah. And so what we need to do here is we need to get this equation to be an x equals blah, 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 blah. Okay, so if we solve for x here, what do we get? All right, so I would have x squared. I could do 4 minus y, and I could say x is the square root of 4 minus y. And in fact, there's a plus or minus. Okay. The plus part, the plus square root of all of that, that gives us this half, the right half. The negative square root, blah, 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 gives us the other half. And so that's how together we use two equations to help us define that parabola. Okay. If I want to choose this distance right here, I'm going to say that that distance is the square root of 4 minus y. So this is the square root of 4 minus y, and then I double it to find the whole thing. That's where I get square root of 4 minus y times 2. And since it's isosceles, we know that the base and the height are the same, so I can go ahead and write that in there. Now, rinse and repeat. We simplify, we take the integral, we plug in our numbers, blah, 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 blah. We end up with an answer. Okay, but as you are studying this material, this piece right here, that setup is like the most important part. Okay. So if we clean this up a little bit, we might notice that this 1/2 and that 2 reduce. I'm going to take this 2 and bump it out to the front. So I have 2 times the integral from 0 to 4. What happens when I take square root of 4 minus y times square root of 4 minus y? What do I get when I multiply those two square roots? 4 minus y, there you go. So this whole problem really boiled down to this. And that I trust you to calculate. Blah, 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 blah. You will end up with 16. Yes, Christina, in this case, all right? But we need to be really careful about like why we chose to use symmetry in this case. But yes, if you want to use symmetry in this case, then you need to put it in terms of x. And by that, I would say this is really in terms of y, because we've isolated the x. All right, so we are definitely overdue for a break. Let's be back at 11 o'clock. Give you a little bit of time to digest and think about all of this, but we'll be back here in 15 minutes to work through a few more examples, okay? We are gonna focus our work on drawing the pictures, the intersections, and the setup piece, okay? The rest of the computation, I trust you to do the computations, but we really need to make sure that this part is very solid, okay? So see you back here in a bit. Okay, so for the remaining time, we're gonna go through a few more examples, 1, 2, hopefully 3. And then if there's any time left over, we can kind of start to preview what we're going to talk about next week. But everything that is in this section that we will cover today is sort of the end of quiz 14. Okay. So let's jump right back in. Okay, so a solid has a base in the form of the ellipse x squared over 25 plus y squared over 16 equals 1. Find the volume if every cross section perpendicular to the x-axis is a rectangle whose height is 3 times the base. So keeping that in mind, let's go back up to the top where we had those diagrams. And let's see which one of those pictures it might match best with, and what we might need to change in order to apply for this particular question. Okay, so we're looking for a solid that has a base in the form of an ellipse. Find the volume of every cross section perpendicular to the x-axis is a rectangle whose height is 3 times the base. So let's go back up to the top. And we've got these 6 diagrams right here. Which one of those do we think best matches example number 3? Number 3, yeah, exactly. So we're looking at that rectangular cross section. So we are thinking that we have a bunch of rectangles coming out from our base. Now tell me about the ratio of the sides to that rectangle though, because when we used this previously in like example 1, we were thinking that we had squares, and so this base was the same as the height. But what do we know now about the base and height in example 3? The height is 3 times the base. Good. So whatever we have here, we would just do 3 times that to get this distance, right? If we have a base and we do 3 times that, that will give us the height, right? Now, one last thing. We had said that this, the bottom of the entire volume, was a circle. How is this similar or different to what we have in example 3? Yeah, we don't necessarily have a circle, but we have an ellipse base, okay? And so let's go back down to the bottom now. We're visualizing again that we don't have sort of quite a perfect circle, but it's more like an oval. We have rectangles where the bottom of the rectangle, if I multiply it by 3, I will get the height of the rectangle, okay? All right, so let's start off with a diagram. So x-axis, y-axis. All right, who knew this was going to be a pop quiz today? Just kidding, it's not a pop quiz, but how do we graph that? X squared over 25 plus y squared over 1, or y squared over 16 equals 1. I think for the STEM core group, this was like maybe September-ish or November-ish. I don't remember. But yeah, exactly. Okay, so good things to remember. I know we've been talking a lot about our parabolas, right? But the conic sections, that is definitely a big chunk in Calc 2. Okay, so maybe let's put a note here that conic sections we want to review. for Calc 2. Okay. And we think about what those numbers mean. And so this number on the bottom means, well, this number on the bottom, since it's underneath the x, means we go out 5 on to the right and to the left, whereas this number under y squared, if we take the square root of it, means we go up and down 4 units from our center. What is our center for this ellipse or this oval? What is our center? Yeah, in this case, we have a center of 0, 0. Okay. All right, so let's sketch a diagram of this. We've got 5 units to the left, 5 units to the right, 4 units up, 4 units down. And we've got a sketch of an ellipse, okay? Now we're gonna be using this to sort of like find volume. When you get to Calc 2, you're going to look at volume. You're also going to figure out like, how do we determine part of the length, like the arc length of things? So that's really where you'll be headed in Calc 2, okay? But now that we have our diagram, and maybe we should list these points, 5, 0, 0, -4, 0, +4, and -5, 0. Which way, according to the question, do we want to draw our purple lines? Yeah, we want to draw these vertically, okay? So if we draw them vertically, like at the very beginning, we would have sort of a very small base. Maybe by the time we got close to the middle, we'll have a bigger base, and then like a medium base, and then like another small base to kind of finish that out. Okay, now the way we know how to draw these is because it tells us that these cross sections are perpendicular to the x-axis. When we get back to class on Monday, we'll be having to make more decisions. How do we know which way to draw these rectangles, these purple lines? And so that's going to be something like a skill to keep on practicing, okay? Now, what does this purple line represent in the context of this question? Okay, so what does this represent? It represents the base of the rectangle, exactly. So base of the rectangle. Okay. So each of those purple lines represents the base of a rectangle. And the height of that is going to be 3 times whatever that base is. So if, let's say, this base right here, how long is this base, by the way? Like the one in the very, very middle. Oh, it's 8. Okay. Let's say that this height were 3. How long is the base of the purple rectangle right there? 6, right? Because we would want to go the whole way down. All right, let's say that this one is just 1. How long is the base of that rectangle? 2, exactly, because we want to double it to get the entire distance, okay? So since we sort of have all the points here and we only have one curve, we don't really need to think about our finding intersection points or anything like that for this particular case, okay? So in this case, I would say that it's not really applicable. Well, if that's not applicable, let's jump right into our volume then. Volume is the integral of area. Do I want a dx or do I want a dy? All right, Graham says dx. If you agree with him, tell me why. Why should this be dx? And if you don't agree with him, tell me why you think it should be dy. Yeah, because they're going on along the x-axis, right? So if we put a dx here, and then we write a note to ourselves that we are stacking along the x-axis, that's how we know that we should have a dx at the end. Now that also means though, for our bounds, we want x values, right? So for our bounds, we want to be thinking x values. So we've got our integral. What are our bounds in this case? Where do we start? Good, we start at -5, we go all the way to +5. All right. Now let's figure out the area formula for a rectangle. What's the area formula for a rectangle? Base times height, great. So we could write base times height dx. But we could also say, I'm going to do two things at once here. Because my ellipse is symmetrical about the y-axis, I'm going to double the integral from 0 to 5. So I'm only going to find the volume of this half, and then I'm going to double it so that I find the entire volume. Okay. And I'm going to write this as base times, what's another way to write height? Three times the base, good. So 3 times the base is the same thing as the height because the question told us so. Okay, and a lot of times the questions will say this is the relationship between the base and the height, so that you can just use that one function and then multiply it by some factor. Okay, now if we said that the height was half of the base, then I would replace this 3 with a 1/2. Okay, so let's see. We pull out all the constants. I now get a 6, the integral from 0 to 5 of base times base or base squared dx. Okay. So now we have to figure out an equation for the base. So we have to figure out an equation to represent this purple line or any of the purple lines. What are our ideas? How might we be able to find the equation of the base? And it might be helpful to look back at example 2 or example 1. But how do we find an equation for that base? it's okay if you don't have an equation. Maybe throw out some ideas on what we could do to solve for it. The y aspect of our equation. Okay, so we have this equation here. What do you mean by the y aspect? Are we solving for x? Are we solving for y? What do you think would be helpful? Okay, so yeah, I agree. I think we've got a y distance here. So maybe let's go back to example 2. So is this a y distance or an x distance? And anyone can answer this, but these sort of squiggly yellow ones that we drew, are those y distances or x distances? These are x distances, okay? And so if we have x distances, then we needed to get x by itself. So we needed to solve for x, or in other words, have an equation in terms of y. Okay, so an x distance meant that we needed x equals in our equation. How do we modify that idea for this different question? Yeah, we need to get a y equal. So we're going to take this equation. We're going to get it in terms of y, or y equals blah, blah, blah. So we have it in terms of x on the other side, okay? Now, once we find that, we'll be able to figure out sort of a positive equation and a negative equation, okay, which together will give us the entire ellipse. So let's work through the algebra. So we've got x squared over 25 plus y squared over 16 equals 1. I'm going to get rid of the fraction because I don't like fractions. I'm going to multiply everything by 400, okay? And that will give me 16x squared plus 25y squared equals 400 because I multiplied everything by 400. Then I think it's a little bit easier to get y by itself because I need to subtract that 16x squared and I need to divide by 25. So I will get y equals the plus or minus square root of 400 minus 16x squared all over 25. Okay. I've got these two equations. The plus one represents the top distance. And the minus one represents the bottom. So how could I find this distance right here using the equations that I have? Right? How do I find this distance if I know I sort of now have a top function and a bottom function? Can you be more specific? Times 2 of what? You don't have to type it out. You can just tell me like which expression you're referring to. Yeah, we can do 2 times that, right? Because we have the top half. The positive equation will give me that part. But if I want the entire thing, I can go ahead and double it. So that means that for my base, I'm going to have the square root of this super gross looking thing. Correct? Incorrect? Yeah, we sure do have to square it, right? So like this right here, this squared, I know that we just did so much work to even find that. But if you forget to square it, you made your life so much harder. Because when we square it, that big square root goes away and now it's a lot easier to integrate. Okay, so a lot of times you might get sort of an intermediate step that's pretty disgusting, but in the structure of the problem, it's actually not that bad. Okay. So what do we have? 6 times the integral from 0 to 5 of 400 over 25 minus 16x squared over 25 dx. All right. You can simplify that, work through your integral, but you should end up with a very large number for the volume of this shape. Okay. So this sort of practice in terms of crunching the numbers is a good chance to review stuff from chapter 5. A lot of the integrals are actually quite straightforward after you set them up. It's just the setup part that's really tricky. Okay, so we've had sort of a slightly different flavor question where we didn't have more than one function, but we were able to use that to turn it into one function and then another function, and use symmetry actually twice in here to save ourselves some time with the computation. Okay. Any questions so far? I think we've actually only got one more question to take a look at here. So. All right. Well then, let's do our last example here, which is example 5. Yes, I would encourage you to do lots of practice, lots and lots of practice and thinking about it, because it's definitely a different way of thinking, especially the 3-dimensional part. Okay. All right, so let's take a look at this last example then. Find the volume of the solid whose base is bounded by the circle x squared plus y squared equals 4. So here are those conic sections again, with cross sections perpendicular to the x-axis as semicircles. All right, so the volume, the base of this whole shape is a circle, and then the cross sections themselves are semicircles. So let's go back up to the top for a moment. Let's pick which picture matches this scenario the best so we can kind of envision it, because we're not going to draw the three-dimensional part, we'll draw the two-dimensional part. So, all right. Which one of these diagrams matches example number 5? Number 1, there we go, number 1, okay? So number 1 is exactly our case because we have a circular base and each one of these slices is gonna be a half a circle, a semicircle, a semicircle, okay? So every single one of those cross sections or slices is going to be a semicircle. Now, is the radius all the way across the base? Is the radius all the way across the base? What do we think? No, okay. What did we say? Yeah, we said the radius was actually half of the base, okay? The radius is half of the base. Let's keep that in mind as we work through this problem, okay? So, all right. So let's draw our picture. Why is this all weird? Let's try this again. Okay, so let's draw our diagram. As I'm setting up the axes, someone tell me about the center and the radius of this circle. What do we have? According to our equation, what is the center? What is the radius of this circle? Center 0, 0, good. And the radius? Perfect, radius is 2. So I'm gonna go ahead and mark or draw this circle. I know it's centered at the origin with a radius of 2. So this is 2, 0, 0, -2, -2, 0, and 0, +2. Okay. All right, and now we're looking for cross sections perpendicular to the x-axis. So they tell me which direction I should draw my purple lines. And in particular, they want me to draw them vertically. Vertical, vertical, vertical. Okay. Listen to this question carefully. What is the radius of the biggest semicircle cross section? Okay. And where does that happen? Good, good, good. So the biggest radius is going to happen at the tallest part of the circle. Now, I'm really glad that you all said that radius is 2. How long is this distance? Like, how long would that purple line be? That purple line would be 4, right? So we don't want to do like we did before, where we find this distance and then we double it to find the whole thing. right? In fact, as soon as we get that top curve, that's our curve. That's it. So each one of these lines then, the purple lines that I drew, what does the purple line represent? What does that purple line represent? Excellent. That purple line represents the diameter of the semicircle. Okay, represents the diameter of the semicircle. So when we think about our area formula for a circle, we need to be really careful because we don't want the diameter. We want the radius. Okay. And so again, because this is sort of like one shape, we don't necessarily need to worry about intersections as much. And in fact, we can go right to our volume equals the integral of area. All right, is it going to be dx or dy? And how do we know? It is going to be dx. Can someone confirm why Ethan is correct? Why is that going to be dx? Okay, because we're stacking along the x-axis. Okay. I want to be really careful about the perpendicular part. Okay. Only because what you said, Ethan, is completely true for right now. Right? Isn't this always like the worst part about math? It's true for right now. However, next week, it won't always be true, depending on the method we use. And so what might be more important is that we are taking the slices and we are counting them along the x-axis. Okay. So in particular, just to kind of put this in your brains for next week, at some point we may draw a picture that looks like this, but it will actually be dy. Okay, so don't worry too much about that right now, but that's the only reason I'm being a little bit picky about that perpendicular piece, because it's not always going to be true next week. Okay, so now that we're worried about that, let's think about this particular problem. Okay, so we've got volume equals the integral of area dx, because we're stacking these slices along the x-axis. And so that means that our bounds in this case should go from -2 to 2, because those are the x values. And it's a semicircle, so we want pi over 2 r squared. And let's actually write this out as radius squared dx. Okay. And so let's do a couple things here. We know that a circle is symmetric, right? We know that a circle is symmetric. So I'm going to go ahead and do two things at once. I'm going to bring this constant out to the front, but I'm also going to change this bottom bound to a 0. Okay. Does that make sense to folks why we have a pi in the front now instead of a pi over 2? Okay. So we have a pi in the front, and now we just need to figure out an equation for the radius, okay? So if I want an equation for the radius, I want to know this distance. I don't want to know the whole thing. I just want to know that distance, or I want to know this distance, or this one, or this one, okay? What do I need to do to this equation to find something that defines this piece? right? So this is a new strategy for us. How do we find a function that defines just that top half of the circle? R squared divided by 2. Why do we have r squared divided by 2? Yes, I want to know how I can define this function. Solve for y over 2. Why are we solving for y over 2? It's actually a really interesting point that you bring up. Why do you say y over 2? Last problem, we looked for a distance of y by solving for y. I would agree. I would agree. However, I'm not sure your reasoning is quite correct. So when we were solving, we solved y, and then we ended up with how many equations on that side? How many equations did we actually find for y? We found 2. Okay. So in particular, the positive one talked about that part. The negative one talked about this part. So when we found our y value, we actually had to think about doubling it, right? We had to think about doubling it. So how does that impact when we're looking at this question here, when we only want the top half? I agree that we're going to solve for y, but let's see what we get when we solve for y. Yeah, we get y equals this, the plus or minus square root of 4 minus x squared. All right, and so the positive one tells me about this distance. The negative one tells me about the bottom part. I don't want the bottom part. I only want half of this. And so because it's only half, I only want to grab the positive one to represent that radius. And so let's go ahead, and in our equations, we've got pi, the integral from 0 to 2 of the radius 4 minus x squared dx. Okay, so in this case, we don't need to double it, because if we doubled it, it would give us the diameter. We only want the radius, so we only want half of that. Okay, and good for us that even though there's this gross square root, since I square it, that part goes away. And so we're left with pi, the integral from 0 to 2, 4 minus x squared dx. All right, and I'll leave you to finish that question on your own time. Great question. So Megan is asking, where did the pi come from? We thought it was pi over 2. Can anyone help out with that? Why is it not pi over 2? What did we do in sort of steps that we didn't write out everything? How did we end up with pi and not pi over 2? Okay. So we did two things at once here, right? We brought the pi over 2 out to the front, but then we also doubled it because of the symmetry. So pi over 2 times 2 just gives us the pi. Perfect, okay? And these are kinds of conversations that if you're looking at an answer key that skips a bunch of steps, I would encourage you to write that out. I would say pi over 2 times 2 gives you pi, right? So sometimes just because there's an answer key doesn't mean it shows all the steps that you need. And so maybe the work that you do is in figuring out how you get from one step to the other, okay? All right, well, folks, I think this is a great place to stop today. I think this content is definitely like big brain energy. Not that it's necessarily like harder than what we've done, but it accounts for a lot of the tools that we sort of been learning along the way and making sure we know how to sort of reason our way through a problem, okay? So we will stop here for today. That covers all the stuff for quiz 14. And next week, which is our second to last week of class, we will dive deeper into finding volume. All right, next week is all about volume in so many different ways. And the big theme, like volume is the content, but the big theme is really around decision making. Okay, so we're going to focus on our decision making. And a lot of that comes from having a good setup diagram, working with the algebra piece, and then setting up that integral. Okay, that's really where I'm wanting us to focus our big brain energies. Okay, so on that note, I'm going to stop sharing the screen, turn off the recording,